Hi, everybody. Thanks for the introduction, Anna. So today we're going to discuss on something different from the previous talk that is more AI in different next generation task or application. This is first a thanks to all the people that have contributed, or at least the team that I'm supervising here at UCL. We are a team that is kind of tackling different topics in terms of application, but all with the common denominator of try to apply learning strategies to large-scale system or networks, and specifically graphs. So today, out of all these topics, I'm going to talk mainly about graph-based learning strategies with the application of generative models for graphs and molecules in this case specifically. And then in the idea of the work we do on autonomous systems, I'm going to discuss a little bit about decision-making strategies. And somehow, in both cases, I will try to have a focus on how these technologies that use deep learning networks that are models that are highly data hungry can be more efficient or fast, which it's a clear bottleneck, data and computational time, and also how we can have a deeper understanding on how these methodologies work. I think that's one great aspect of the academia, that we can go deep in the understanding of the methodologies, and even if deep learning is a black box, actually it might be not that black box, right? We can understand a little bit at least why things happen. Maybe not fully how, but at least we can get a sense of it. So I'm really interested in this understanding. So let's start with the generative model. Well, you all know the generative models nowadays have kind of invaded our space. So this is, for example, an astronaut dog generated by Gemini, and these are faces that are not people that do not exist, right? So this is well known. We all use these and LLMs. The question is, can we also generate graphs? So can we also generate molecules instead of text or instead of images, right? Is it the same, or what are the new challenges? So that's the focus on our work. So how can we have a bunch of, sorry, the resolution is not great with the screen, but basically we have a bunch of molecules. So how can we learn the rules or the statistical properties of these molecules such that any kind of LLM could ideally start from a point and generate a real molecule, ideally with even some properties. So why it's challenging? Because usually we work in Euclidean space, where we know, for example, how to connect 2 points in the shortest path, and etc. Is different when we have non-Euclidean spaces, so we live in a manifold. Also, when we look at generation of images, for example, we kind of perturb features that are pixel intensity, for example, right? Here, in the case of molecules, we have features on different nodes, but also the topology. So how we do perturb both, or should it be independent? How do we do it? It's not clear. Also, we have 2D views that we usually work with, but when we want to look at activity or pocket binding, you actually look at the 3D conformation of your protein. So how do we actually generate 3D as well? Oops, sorry. And also, all the different graphs have very different sizes and can be also very high dimensional, very large. So all of these, they're very difficult challenges to solve. So what we do is to try to understand first, how do we do it specifically with an application in mind, drug discovery? So we don't want to generate valid molecules. We want to generate molecules that can become drugs. So what does it mean? Then we also try to look at the understanding part. So how do these generative models actually work? And if they don't, why? And also a 3D generation, which I don't have the time to talk about that today, but we also have a little bit this as a kind of the 3 main directions across which we develop our research. So in terms of can we generate real drugs, we have that the drug generation is a very, very long process of years and a lot of money. And there is an initial part of this. Yes, it's the same, yeah. There is an initial part of discovery in which there is a lot of human intervention to design initial points for these steps. And the question is, can we have machine-driven intervention instead of human intervention, right? So can machine learning help in this initial discovery that is the starting point from any drug pipeline? So what does it mean? It means that if we have a massive database of any molecules. Usually what happens is that there is a screening, and we only have some molecules that are called hits, that are very simple, that are selected by the human. And these are then, along the process, they become more complex, because if I want maybe an activity, I know that I need to add these components, and then maybe if I want a given other optimization, I even have another further components, right? So everything starts from this hit. So the question is, instead of generating any possible molecule, can we generate a specific hit, so a starting point for this process? Because this process will happen. So things will never be perfect at time one. So if I want a specific activity on a specific target and a specific low toxicity or any type of behavior, we will need to massage this starting point, this hit, right? So that's what we have as a goal. But what happens today is that ML people, so what we really wanted to understand is how ML tools can be really useful for people that want to develop real drugs, right? And today we, as a, not all, but most of the research stops here. So can I generate, with current models, valid molecules? And we get 99% accuracy. So you feel there's no more research to do. But then instead, if you actually ask, okay, but if I want to have an initial point here, a hit that is really a good part, a good starting point, could we do that? So can AI really generate a good hit, right? So that's a work that we look at. So I will skip here the details because it's more the pipeline we built, but basically we kind of select some filters and we test the current generative AI models to understand how they're good, how do they do, not here, but in evaluating specific molecules that have to kind of respect some filters and have to have a good docking score. So they have to say, if I want this to actually dock well, so fits well in this pocket, bind well with this pocket, that would be like showing activity, how do they do? So can we have molecules, not that are valid, but they are good here. So they really have good properties, chemical properties, I can show some activity. And the question is really to also motivate to also understand that this 90% is not the end of the story. So if we take these models that are very, very good at generating valid molecules, and then we see in a latent space plot where the greens are the desiderata, so the molecules that we know that, the points are active on the target that we have in mind in this case. We actually see that these 90% models generate points that are more here. And only few of them are actually finding the right structure or being able to actually have the right combination of chemical properties such that we can get good activity. So that's something that we kind of add as initial steps to understand if current models are good enough, if we have a real application in mind. So if we want to have some specific activity. So this is the initial part. We also identified some of these few ones that points, yellow points that are actually overlapping quite well with these other desiderata points that assumes they have good behavior. And now we are testing them in the labs. This, for example, is one of the generated molecules that we are testing. We are still waiting for the results. So the ultimate point will be, one thing is to have an exercise of validity. So can the model generate something that resonates well enough? One thing is, can we generate something that passed the labs test? So we wanted really to have this understanding. And now, kind of the previous plot shows that there is more work to do, because ideally when we fine-tune the model to generate something that is active on a given target, so to replicate these green points, we see that there is kind of more work to do, because everything is actually stays in the center. So in terms of properties we are looking at, they're not the same. So that's why we had the second step of understanding, that is, okay, why we don't get the same behavior, or what should we do to have better generative model? So as you know, well, I don't know if you know, but in case you don't. So generative model, for example, the diffusion models, how do they work is I take an image, it's actually very simple, and I add a small perturbation noise at each time step till the point in which I reach a full noise image. And then I train a neural network to reverse this process. So to have a step-by-step denoising, such that from any point that I sample from a complete random Gaussian distribution, I can generate the image that I'm interested in, right? So that's what happens. Basically, if I have a data that is my cat's images with a given distribution, I perturb this till I reach a Gaussian distribution, that would be this one, and then the model simply learns how to reverse back its trajectory. So I will skip here the details because it's quite theoretical steps, but what we try to understand is how to build this trajectory in Euclidean space is kind of understood. So the question is, how do we do it in non-Euclidean space? So we try to use the optimal transport, that is the similarity between two distributions, but for non-Euclidean spaces. So that's where the theory comes from. But just to, exactly, so instead of, well, let me skip because I think how much? 2 minutes? Wow, okay. Okay, so we basically have a better performance and convergence, but I will skip that. Okay, so for this, I think I will just give you the intuition of what we do because I only have 2 minutes. So indeed, so we also work on reinforcement learning. And even here, we kind of aim on understanding the data efficiency and the explanation of how things work. So RL is a very powerful methodology and technology, but it's very, very data hungry. And the question is how to make it more data efficient and how to scale to real-world complex tasks. So even here, we had a better understanding, better tools, and a better algorithmic perspective. Just let me say that in RL, for example, most of the time you use games as a kind of reflection of what happens in reality. So you may want to have an agent that needs to explore a maze or a labyrinth till it doesn't reach, for example, a gold or a good reward. So the first analysis was, okay, this problem theoretically is solved, how to explore this space such that I found the golden point in the shortest time with the least number of steps. But in deep RL, we have different ways in which we can explore this maze, for example. These are all different algorithms, and the heat map shows the frequency in which we explore states. And these are really different. So how do we understand these differences? Which one is better, is best? And why, in the theory, this is kind of solved, how to explore this, but in practice, in deep RL, it is not. So we kind of have a theoretical study that let's say, the tabular and the linear approximation of RL. It's kind of known theoretically. The deep RL, it's not known. So we kind of have a middle steps of kernel-based RL to study the data efficiency. So how much data do we need to explore the environment well enough? So if I have these n states that I need to explore, how many iterations of exploration should I do to get a good understanding of the environment? Okay, we also try to understand if another aspect is, since the exploration usually starts from tabula rasa information, and we now know that LLMs are kind of good in giving intuition to human, and this intuition sometimes would also help a lot in data efficiency. So if I have a door and a key, I immediately know that I need to pick up the key to open the door, right? While the robot does not in RL. Can we use this intuition that we have as a human, so can we use the LLM as a proxy for that to improve this exploration? I think I'm done, right? Okay, that's it. Then we also have like a new solver that we use to also have any RL environment much faster in terms of computation. But let me close it here because I told Anna Maria that I would have been less than 15 minutes, but I'm more. So this is just a summary, and the point is, contribution is more toward understanding the applicability of generative model to actual drug discovery and how to have a better understanding, both in generative model and in RL, and how to develop faster tools. Thanks.
Thank you very much. Questions? Any questions? If there are no questions, I have a question, but this is more like a sort of ethical question. So there are a lot of worrying around LLM, right? And it looks like, as you pointed out, there is no limits of the applications that we can have on LLM. So in your opinion, what is the limit, and should should we be worried?
Let's say that I don't use, I use a little bit LLMs, but I don't use it too much. So in terms of generative model at large, you mean, or LLM specifically, like LLMs on ChatGPT?
In
Yeah.
general, yeah.
I think as long as they are supervised, then they can have a lot of applications, I agree. The point is always like there can be hallucinations, so how to prevent that?
Yeah.
So that's, I think it's the main limitation that we should be careful about, the hallucination of these models.
Yeah.
So yes, thanks.
Thank you, Laura. Other questions? Yeah, there is one here.
Hi, thank you for the talk. I have very little experience with this topic, so I'm not going to ask you a technical question. It's a bit exotic, but maybe you can draw a link. I was wondering, when we use some of these tools like LLMs, or maybe also some tools which are related to the first models that you presented, and in particular I talk from the perspective of a researcher, we would like to have a tool which can help us with research, right? So, for example, most of the time we read lots of papers. In reading these papers, we hope to find a problem to solve. And so once we have found it, we have to understand if it's really relevant or not. So there's lots of effort in sorting out problems and then developing ideas to tackle these problems. Now, this seems to be somewhat related to what also you are trying to achieve with the first model. Mm-hmm. I mean, of course, it's different applications, some different concepts, but I suppose there is some link. So my question is, can these first type of models be used to create tools which can help us in research, so in the broad scope, not for a specific task as developing drugs? And if yes, how far are we from being able to have such tools?
So I'm not sure I fully understand. So you mean the first work in terms of the generative models?
Yes.
Okay, so if they can help toward research?
Yes. So specifically, in doing the type of task that we as researchers do. So it's reading paper, finding problems, okay, elaborating ideas to tackle these problems. To conclude, since for example, ChatGPT seems to be quite ignorant and able
so I think that's a very interesting question. I think it's indeed related to the aspect of can we build an agent that is able to formulate hypotheses and help us in these research steps, which I think it is not there yet. It is for sure the next frontier. So adding a little bit more of reasoning on hypothesis, validation, and testing, and understanding these steps. And I think for sure is a direction in which they are trying to go toward, if that was an answer to your question.
Sure. And do you think your type of generative models can...
I think it is, as long as you frame your problem more as a graph. So these are more specific generative model for graphs. So if you put like reasoning and context in the knowledge network, for example, or aspect like that, then maybe yes. But indeed, you have to put in that modality. So some sort of what the nodes are, maybe concept, and you want to kind of create some connection to that and generate in that sense. Otherwise, I think it might be difficult.
All right. Thanks a lot.
You're welcome.
Thank you again, Laura. And yes, thank you again, the speaker. Thank you.